Welcome back everyone to the last bit of part 2 and then the upcoming part 3. I hope the simulation did finish for every one of you. When it is finished, again the result viewer opens, and for the elastic properties you see an isotropic approximation assuming the material is homogeneous in each direction. We see a Young's modulus and a Poisson ratio and shear modulus, Lame modulus and bulk modulus. Since from the pore analysis and the permeability analysis we knew the structure was kind of anisotropic. So if we scroll down, we see an approximation of the isotropic error of 21%. Elastodict looks at the anisotropic elasticity tensor and approximates how good this Young's modulus is fitting to the tensor. And it says, red, be careful, the isotropic approximation is not the good one. We can go to the orthotropic approximation and see that the Young's modulus in x, y, and z direction is in fact different. And here we see that the orthotropic error is almost 0%. Yeah, we can go for the orthotropic approximation, which is an approximation in x, y, and z direction. Elastodict also shows you transverse isotropic approximation, and more down you see the anisotropic elasticity tensor. This tensor is calculated by doing 6 different load cases, 3 tensile experiments in x, y, and z direction, and 3 shear experiments in x, y, y, z, and x, z direction. With that, Geodict calculates the effective elastic properties. Again, you get plots for the direction-dependent stiffness, and you can visualize the strain stress result files similar to the visualization of the flow or the heat results. Being finished with analyzing the sample, we now are going to build a digital twin of this metal foam. For that, we will do a modeling step, and then we will validate that we have in fact a digital twin and compare the simulation results to the results of the metal foam CT scan. The goal of part 3 is that you will know how to generate a digital twin with Geodict of a foam structure using GrainGeo to represent the pore geometry, FoamGeo, and manipulating the geometry by using process geodilating and eroding. For that, we head to Model and GrainGeo. We click Edit, and now we choose a voxel length representation of micron. It's just that all length units are micron in this window. So we choose the rather small geometry of 120, 120, 120 and 12.99 microns. The idea is that we will generate a rough resolved structure which will go fast because we have a small domain and then resample the structure by a factor of 3 to 360 and a voxel length of 4.33. For the generation, it is important that we have a periodic structure and that we remove object overlap. We select 0.5 and we deselect the other 2 boxes. Since we know that our CT scan had a solid volume fraction of 16 to 17%, we select here a solid volume percentage of the inverse, so 84%. For the objects, we delete the sphere and we want the ellipsoid to have a relative volume of 100%. Now comes the idea that, let me close this window, you stay in this window. Let me load the identify pore result. You see we have shortest, intermediate and longest diameter. So we have maximum, minimum, mean value, and standard deviation. So we can give stochastic deviations to the ellipsoid diameters. And we also can give an orientation to the pores. So we click Edit and Objects Options, and we now enter the values for the diameter 1, which should be our longest diameter. For that, we choose the log normal distribution and enter 356.6, 25.9, 295.4, 405.7. We click OK, and we head to the intermediate diameter. We click Edit, we go to log normal, we select 310.3. For the arithmetic standard deviation, we enter 27.9, 238.7, 345.9. Okay, and we go to the last, the shortest diameter. We choose the log normal distribution and we enter 256.0, 25.8, 193.2, and 299.0. And we click OK. Now we still have to set the orientation of the pores, so we click Edit. We choose anisotropic orientation and we choose the orientation tensor. And now it gets a bit boring. We enter 0.5821, 0.1048, 0.0727, 0.3447, minus 0.0826, 0.0732. I will just wait a few seconds that you can finish typing those values. Okay, we check that the object overlap is ID1 with ID1 gives ID1. If this is not the case, please make it that you select overlap rule 1, that 1 with 1 gives 1. Okay, and now we can generate the structure. And since I previously created a crane structure in the same directory, Geodict asked me, do you really want to overwrite the structure, rename it, or backup it? Since it's some other result, I will just overwrite it. If you are overwriting your structure, please make sure that, or if you're overwriting your results, may it be structure generation or property prediction, please make sure that you really can overwrite it and are not overwriting different results you still need. If this structure generation is finished for me and not for you, you can just click this stop button and select yes. It will stop the structure generation at this point. You might have some more residual overlap than me, but this will not influence your digital twin too much. If it's finished for me and not finished for you, just click stop and then yes, and then it will be fine. For you, for everybody else, you wait until it's finished. It's giving me warning that some residual overlap is left. Everybody else, please click now stop down here and then confirm with yes. And then Geodict will create a crane structure similar to this. Now the next step is that we check the camera. We can again disable and enable the halo. The next step is that we right click on Get Objects and select Edit Domain. Now we will resample the domain. Since all those spheres are given as analytic objects, they are described by a center point and a radius. And for ellipsoid, center point and 3 diameters. Nothing else. We can resample them to a higher resolution by just changing the voxel length and the domain size. So if you want to have a 3 times better resolution, we increase the structure by a factor of 3. So 360, 360 and 360. And for the voxel length, we have to decrease by a factor of 3. So in this case, 4.33. And we click Run. Now we have a high resolution structure, which will be our pore geometry for the foam. So now we go to Model and select Foam Geo. We go to the random foam model and click Edit. Here you can set a domain size. Since we will make it based on this geometry, we ignore this and we select here Create Pore Geometry. We click on this and select Use Current Analytic Geometry. This will disable all those options because it will get the information from this structure. For foam options, we select Angular. We know that it's an open cell foam, so we disable the closed cell foam options. If we select that we want to give a given solid volume percentage, we set the strut thinning factor to 0.3 and the solid volume percentage to 17. We click OK and we click Generate. This will take again now 1 to 3 minutes depending on your computer. We are currently in the last steps of the foam generation. And we are done. Again, we are greeted by the result viewer giving us information on the solid volume percentage and the information about the strut length or the phase areas. And we see our currently not digital twin. We will now make those angular struts less spiky or pointy. For that, right-click on Structures and you select Erode Structure. Here we select an erosion by a factor of 3 voxels and we click Run. Now Geodict will just remove the first 3 layers of voxel from the structure and you see it got thinner. But now we will do the reverse operation. We will right-click on Structure, select Dilate Structure. We want to dilate the material of ID1, which are our struts, with coating material of also ID1. And we want to dilate by a factor of 3, and we click Run. Now Geodict added 3 voxels on the structure, and we see the struts are now less edgy or spiky and more round. I boldly claim now that this is our digital twin. Now we want to validate that this is in fact a twin. The first step is we look at our identify pores and compare the pore statistics. For that, we go to Analyze, Porodict, and select the Identify Pores and click on Edit. In that case, since we have generated the structure periodic, we have a periodic structure, we can uncheck this option and say, hey, everything is periodic. Then we click OK and we click Run. Now again, we are greeted by a warning. Hey, do we want to overwrite the files, rename them or backup? And in this case, we really want to rename them. We rename to _ digital twin because otherwise we would overwrite our previous Porodict results. And we click Rename. And again, a pore analysis is done. We can have a look at the results again and see the number of pores, the contacts, and the pore diameter statistics. Now, if we press the Control key of our keyboard and click on the other Identify Pore, the previous result, Geodict opens the result side by side. On the left side, the one which is the top, and on the right side, the bottom one. So the right is our digital twin, or presumably digital twin, and the left side is our CT scan. If we compare the mean values of the shortest diameter, we see, okay, 256 to 260, very close. 310 to 307, very close. The longest diameter is very close. Also, the standard deviations are close, and the other values too. You can have a deeper look if you do the workshop again, if you like. Also, the orientation tensor shows the x, y, and z values are close and that we have an anisotropic orientation, preferably in x direction, a bit in y direction, and almost no poor orientation in z direction. Now we can also click on Combine Results and just click OK. And now we combine those two GDRs of porodict identified pores into one, which will now allow us to compare the plots, for example, of the diameters, where we see they are close, or the sphericities, or the orientations. It seems that the structure, or this modeled metal foam, seems to be a digital twin for pore characteristics or pore size distributions. Now we also check the performance of the foam for thermal conductivity. For that, again, we go to Predict and select Conductordict, and we have the thermal conductivity. This time we remember to set the heat result underscore digital twin. We click OK and we click Run. The heat result of X direction is finished almost now, and now we will get the simulation in Y direction and then Z direction. Again, this might take about now additional 3 minutes. And we are done. Let me just load the heat result from before. And now again we can right click, hold the Control key of your keyboard and select both heat results and compare them side by side. And see that they are pretty close together. Looking at the time, in the handout it's described in detail, doing the same simulations as before for the percolation path, for the flow simulation, for the tortuosity, etc., etc. It's described in detail in the handout, so if you would like to do it, you can do it. For this workshop, the time gets close to the end. Since the time is getting close to an end, we will now have a short recap of the workshop. As a summary, in part 1, you learned how to import your CT scan or your image data into Geodik and apply basic image processing like cropping or a sharpen filter, and then segment your structure to turn the gray value images into binarized information of your structure. In part 2, we did various pore analysis and physical analysis of the structure, looking deeper and gaining insights on the foam scan. And in part 3, we used the insights from part 2 to build a digital twin and compare the results of the twin to the model. In part 1, you had the image processing and segmentation knowledge, but also some basic knowledge like setting a project folder or loading 3D image data or volume fields. In part 2, I briefly explained how to reset Geodik and load a structure and showed you how to draw pore size distributions, calculate open and closed porosities, calculate percolation paths, and also calculate physical properties like the permeability and the tortuosity, and the effective elastic properties and conductive properties. And in the last part, we built a digital twin by first generating a granular structure with GrainGeo, which represents the pore space, where we used the previously gained pore size distribution results. Based on this structure, we resampled the structure to a better resolution, which is a good thing to know, that you can generate structures with a rough resolution, which will be faster, and then resample the structure to a larger domain, to a higher resolution, and have a high resolved structure. And on this high resolved structure, we created a random foam based on the pore size distribution. Also, we manipulated the structure. We tweaked it to make the edges more round by dilating and eroding the structure. And after that, we validated the grade of the digital twin by doing the pore size analysis and the conductive properties again, comparing them, seeing they are close together. And as a lookout, with a handout, you for yourself can do the analysis of the other parts too and compare the digital twin with the CT sample. Thank you for your attention. Do you have any questions or suggestions? You can directly contact me. And also thank you very much to my colleagues Martina and Tabea, who helped me prepare for this workshop. Thank you very much. Thank you for your attention, and goodbye.